So at the end of the last video, we were discussing how to graph this function, and I just wanted to say a bit more about that. The method presented here, I'll actually carry this through in the calculator. So if we enter this function, this quadratic, and then go to zoom and zoom standard, what that will do is choose a 10 by 10, or a box that goes from -10 to 10 to +10 to -10. That's what zoom standard does. So you're not guaranteed to get a great picture with that. It's just a standard window to look at. We get some kind of a picture, and then from there we can actually kind of mess with our picture to get a better one. So in this case, do zoom fit after you've kind of straightened this up a bit. But we already got a decent graph and completed the calc max of this, so we already know what our maximum point is, so we can go ahead and let's talk about some general characteristics. So overall behavior of this function, as a pure math function, the domain of this is all real numbers, -infinity to +infinity. This is basically always true for quadratics. As far as their full domain goes, so this is not application domain. So in other words, as long as we're just looking at this as a math function that doesn't have time as a variable or something like that, the domain's going to be all real numbers. But it's very common that we restrict this in terms of a word problem. What about the range? The range is, since it's opening downwards, it's going to be from -infinity up to the y-coordinate here. So the y-coordinate of this it's 37.5. So that means our range is -infinity up to 37.5. If this had been an upwards facing parabola, the range would be from the y-coordinate up to +infinity. It's increasing at a decreasing rate from -infinity up to 3. This is 3 here. So basically from here over, it's increasing at a decreasing rate. And then when we hit the turning point, we are now decreasing at an increasing rate from 3 to infinity. So decreasing at increasing rate. This is increasing at a decreasing rate. All right. Finally, this particular function is concave down everywhere because it's opening down. If it would have been opening up, it would be concave up everywhere. And that's just some general statements about the behavior of the function. Now, as I said earlier, we can tell a lot about the parabola from the leading coefficient. The leading coefficient a of a quadratic function, it determines the direction that the parabola opens. If the leading coefficient is positive, then it opens up, in which case the graph is concave up and the vertex is the minimum point, like so. Whereas if a is negative, the parabola opens down, the graph is concave down, and the vertex is the maximum, like so. So since we've covered this already in a little bit of detail, this is just making this official, so I think we can move along here. Okay, let's talk about zeros and intercepts, x-intercepts. So first of all, some terminology. A real number 0 is the same thing as an x-intercept. So this is equal to an x-intercept. It's just another name synonymous for an x-intercept, and that's a place where the function crosses the x-axis. The x-axis. So a 0 is where you cross the x-axis. For a quadratic function, we have some restrictions in this. So basically, a quadratic can have 0, 1, or 2 x-intercepts or 2 zeros. So, very often I'll say you can have, how many zeros does this have? So you can't have 0 zeros or 1 0 or 2 zeros. So as you see here, here is a 0 zeros. Here is a, whoops, that's supposed to be a 1 0. I didn't do that. That's the hardest one to draw. A 1 0. You basically just tap the axis, the x-axis, and then you come back up or go back. I'm drawing them upwards facing. These could also be downwards facing, so you could have this, that's 0 zeros, or this, or 2 zeros would be like this, or like this. So there's a 0, there's a 0. Two places where you cross the x-axis. And that's it. Those are your only options. 0, 1, or 2, because just think about geometrically, there's no way for a quadratic to have more than 2. For example, in the quadratic that we've been working with, let's go back to our graph of that. If this will turn on. There it is. How many zeros do you have? Well, I have 1 here and 1 here. How do I find them? Well, there are multiple ways to do this, but for our purposes, the easiest way is to use the second calc 0 function. So it says number 2 is 0. And you're going to have to do this twice because we have 2 of them. Actually, you know what, before I do that, let me change my picture a little bit to make this a little nicer. I'm just going to do zoom fit so I can have the whole thing in the picture. Alright, so I want to find this 0 first, so I go to second calc 0. It asks me for left bound, so I need to move my cursor to the left of that 0. Sometimes people get confused about this, about what it means to be to the left, because I'm going to go underneath it and to the left. See, this is to the left of the 0. Hit enter, and now go to the right of that 0, which happens to be above it and to the right. And then my guess is about right there. Hit enter a third time. And there we go. I have the coordinates of that 0 are -2, 0. Now the other one, we have to do it again. So we go to second calc again, 0 again. And now it's a little bit of a pain. I've got to scroll all the way back to the other one. So we'll get there eventually. I think it's a lot of a pain, but whatever. Alright, we're getting to it. Okay, now I'm to the left of the other one. Now I go to the right of that one and take a guess at it, and I get 8, 0. So these have nice integer coordinates. Okay, so those are our zeros. Now, this is I've used the calc 0 method, but there are other very well documented ways of doing this, and you probably know them already, or at least some of them. The principal one is this guy right here, the quadratic formula. So this is a purely algebraic way of finding the zeros, and it again uses the coefficients, and the zeros are given by -b plus or minus the square root of b squared minus 4ac over 2a. So this is great because it always works. You don't have to have a calculator for it. So in this case, I'll just quickly set one up. So -b would be -9 plus or minus the square root of 9 squared minus 4 times a times c all that's under the radical, over 2 times negative 1.5. Now if you run this computation, and notice that this is a plus and minus, so you actually have two answers here. One of them will be negative 2, and the other one would be 8. Okay, but it's a bit more involved to do this, so for our class we're pretty much going to be not using the quadratic formula and generally using the Calc 0 method instead. But I do want to point out that this is a fantastic way of doing this, and if you're anywhere but a situation where you have a graphing calculator, this is what you would do. There is actually even a third method, which is called factoring. Factoring only works in some cases. You know, that's when you break the quadratic up into factors, and you look for numbers that multiply to give you the middle coefficient, and multiply and then add to give you the appropriate coefficients. I'm not going to go into that in too much detail at the moment. I'm just mentioning that factoring, I haven't forgotten about factoring for those of you that know how to do that. Okay, so we've already found our zeros here, so we can skip this. But if you want more in-depth directions, go back to this slide and take a look at them. Okay, let's look at another problem. This is a quadratic, identified as a quadratic, and then we're going to find a bunch of stuff about it. I can tell you a couple of things about this already. This is positive, so that means it opens up. Okay, so it's going to be concave up everywhere. So actually, I already answered part E. So we did that kind of right off the bat. But to find the intercepts, basically, and the vertex and the domain and range and so forth, I need to graph it and see, like, does it do this, or does it do this, or does it do neither of those? So let's graph it and see what we got. Sin x minus 42. I'll go with my zoom standard here. Let's see what I see. Okay, so from that I can see that I need to like reel it in and go down. So I'm gonna go like, where is this approximately? This is like 2 or 3, and that's like 1, 2, 3, 4, 5, 6, 7. Let's go to like negative 10. Let's go from negative 10 to 3, and then do zoom fit with that. Okay, I think I can basically see everything. I might need to come down a bit more just to make this easier to work with. Let's go from y minimum. Let's go to negative 100. And that way I'll have some breathing room down here. So my x-intercepts, that's one of them and that's one of them. So I go to second calc 0. Left bound, I'm going to find the leftmost one first. Almost there. Okay, left bound, and then right bound, and then my 0 is approximately there. And so it's at negative 7, 0. So one is at negative 7, 0. And let me find the other one. I'm going to pause the video here so I can do this off camera. So to find the other 0, I need to go to second calc 0 again and move my cursor all the way over here. So let me pause the video so I can do that. Okay, so I move my cursor all the way over here for my left bound. And now for my right bound, let me go above that 0, which is about there. And I take a guess right there. And I get 2, 0. Okay, so I've got my x-intercepts. Now I want the vertex. So I go, in this case it's a minimum. So I go to second calc, min, and move our cursor again. So I'll pause so I can do that. I move my cursor over here to the left bound of the minimum. Now I'm going to move it to the right bound of the minimum. And then my guess is here. And it's calculating, there's my minimum. we'll finish this in the next video.